All right, so now that we have learned what a random variable is, and as well as learning how a population can be represented, a population data can be represented by a random variable. And so now it's a good time to learn how to find the mean value of a population. And so namely, we call that it's a population mean value. Okay, and so to have a solid understanding, allow me to go back to data one more time. So back into my data one that I had on my computer screen here. And so initially, from start, we looked at data one as a complete list of data values. So it started out given out as an unorganized data, and then throughout our work earlier prior to this point, we worked a lot of time with the sorted version of data one. And further, just very recently, when we start learning about a random variable, or a little bit before that, when we learn about categorical data, then we reorganized the data one into a table where it's listing value distinctively with relative frequencies, and consequently these became the probability. And so in our most recent study, we're learning about a random variable. So here I'm going to let capital X represent a pulse rate for a female. And so these distinct values, any of these distinct values here has a probability. So we've learned previously that a table like this is being regarded as a probability distribution. And so that's just a couple reminder. So in the end, let's try to apply how we can find mean value in this data one again. Now, remind yourself that we actually have had mean value for data one already. So data one long ago, we've learned throughout past lectures, we've found that mean value of data one equals 76.3. So really my aim is not to reinvent or is not to rediscover this value. We've had it long ago, it won't change. What we are really going to be looking at is how we can come up with a completely brand new method to find the mean value. So, but as everybody have already knew, finding a mean value anytime here has to be, we must strictly, even if it's a population data, but we must strictly add up all the values and divide by how many there are. And so before we can even go even further, I have to make another line here. Now, apparently, I made it clear in earlier part of this lecture that data one is not a population data, but maybe in a situation like this, where we're learning a new concept based on this, let's pretend that data one is a population data. Meaning, for some magical reason, we actually know that the entire population of female pulse rate out there, there are only 40 pieces of pulse rate, even though it's not really realistic out there for a population being that small, but let's pretend, and that's why I'm saying just pretend that data one itself is already a population data. And I should have had that word data there. Okay, so now to start with our journey, let's roll back again to remind ourselves about how we can find a mean. Doesn't matter if we are working at a small sample data or being a large population data. Finding mean value is always the fixed fundamental. The permanent fundamental here is that we're going to add up all values, and since we have the data one started out with 60s, so we have 3 60s, so I'm going to go 3 times 60. And then I'm advancing over to the next data values, which is distinctively 64. But I need to add up all the 64s. So there are 4 64s there. So that would be to write 4 times 64. Then I'm moving on to the next distinct data value, being 68. And there are 5 68. So instead of writing 68 plus 68 plus 68, I'm going to write 5 times 68. And so now everybody viewing this, anyone who's viewing this video, is starting to see where I'm going. I'm going to keep adding the rest of the value entries, the values with their own frequencies. So 72 here is happening at frequency 8. So 8 times 72 plus So now I'm going to have 6 times 76. And then I'm going to have the next distinct item here is 6 times 80. Then I'm going to have 5 times 88. And I'm going to add with 1 times of the 96. I'm going to also add with 1 time of the 104. And I'm ending my list here with 1 time of the 124. So that's how we're setting up all the adding of all values, and then finding the mean value. We need to divide by how many there are. And so even though we have a small number of data values here, but let's pretend that our data is a population data. So, and imagine if it really was a population data, that's still the way how we're doing it. We've added up all the values and divide by how many there are. And so in this case, now, admittedly, we already have the answer, so I'm not going to bother with what's the answer of this calculation turns out to be. What I need to bring up here is that I'm going to show a way how we can break this fraction, break down this mathematical operation here, this large expression here into the different expressions, so that we can recognize a new method to find out population mean value. Okay, so after producing a little more space for myself, so this is the next thing I'm doing. This current expression, what it is it's a fraction of multiple terms and being divided by one common denominator. So mathematically speaking, it is completely legal that we can break it down, break this large fraction down as a 3 times 60 over 40. And that's my first term. And then I am going to continue breaking it down further. I'm going to add to 4 times 64 over 40, and I'm going to add again with another term. The third term here on my list is 5 times 68 over 40, and the next one in my list is 8 times 72 over 40, and I'm going to have 6 times 76 over 40. And then as I'm continuing, anyone who is viewing this should be understanding where I'm going from here. So I'm also going to have my next term is 6 times 80 over 40 plus 5 times 88 over 40, and that's completely mathematically legal, plus 96 out of 40 plus 104 out of 40. And the last one here is plus 124 out of 40. And so, of course, at this point, we still haven't seen anything much other than just some algebraic re-expression of our starting fraction there. But how about in the next step here, each individual little term here, each one of these little terms is a fraction itself, and inside of each fraction here, there's a product in the numerator again. So each fraction here, I am going to purposely rewrite, and like I said, everything I'm doing here is completely legal in terms of a mathematically legal right here, meaning it's completely allowed in math. It's a well allowed mathematical operation that we can rewrite this first fraction here as a 3 out of 40. I'm going to group that in one fraction, multiply with 60. So I did this on a purpose. We could have done the other way. We could have also done 3 times 60 out of 40, but I have a different purpose. So the same fraction here, I'm writing that as a 3 out of 40 times 60. And now I'm going to advance to the next term here. My next term here is going to produce for me, so 4 is the frequency count. I'm going to put that purposely over my total n count, so 4 out of 40 times 64. And after writing out a few terms, I hope whoever viewing this video is going to start recognizing what I'm doing here. And so my third term, I'm going to purposely breaking it down as 5, which was the frequency count, divided by 40, and multiply that by 68. And then the fourth term, in the fourth term, I'm going to break it down purposely as 8, which was our frequency count, and over the n number. And we are going to multiply by 72. And so doing it this way, eventually I'm going to run out of space quickly. So I'm going to leave a few dots in between here, but basically we keep repeating this until we hit out a few of our ending guys right there. So 96 out of 40, really the frequency for 96 is a 1. So that fraction 96 out of 40, even though it's already one fraction, I am going to purposely rewrite that as 1 for the frequency of 96 over 40. So 1 over 40 multiply with 96, the value. And again, I am going to re-express that 104 out of 40 as a 1, the frequency count, over 40. And I'm going to multiply with the value 104. And my last one on the list here, 124 over 40, is of course 1 over 40. And I'm going to multiply with the value 124. All right, and so now at this point, here's my explanation, what I have done here. So after we've seen how we turn our data 1 into a probability distribution, then I need you to look back at that understanding and compare with what we're doing here. So each of the term here currently comes out from one part of this product is being the value that's on my table. So look back at my table here. So 3 out of 40 is the probability. Now we call it, it's a probability. Previously we called that the relative frequency. But so 3 out of 40 or 0.075 is the probability where x, the random variable x, takes value 60. And so as an explanation for 3 out of 40, now I'm seeing that as the probability where random variable equals 60. And that probability there is to be multiplied with 60, the actual value of the data in my first entry of the data table. And so along that way, let's have a different explanation. So this 4 out of 40, what I see about that, what I understand about that, now it should be in our new understanding. This is the probability where your random variable equals 64 on this, according to this probability distribution. And 64 itself is the value. And so what's been happening in the two terms here is that I took the corresponding probability multiplied with the actual value on the probability distribution, and then navigate and then move on to the next entry over here, the value multiplied with probability correspondingly. And so once again we can see that in the third term right here, what happened, what was going on in that term is we had this 5 out of 40 is to be understood as the probability from our probability distribution when x equals 68, and we need to multiply that probability with this actual value 68 in our probability distribution. And so that's, if you look through the entire remaining terms right here, it is exactly the same anywhere I was doing the term here. Any of these products came out as a probability. So this is, for example, probability when x equals 124, and I need to multiply that probability with my actual value on the left hand side, 124. And so now at that point we are ready to recognize a new formula to calculate mean value. And so now let's summarize our understanding as far as how we came up, as far as what we came up with as a new formula for the calculating population mean. So generally speaking, anytime we let x be a random variable or an RV right here, and of course x being a random variable is to represent a population data. And so in a probability distribution of x right here, left hand side column, we're listing out the distinctive values, the distinct values of your random variable. So your random variable is maybe recognized to have values distinctively x1, x2, x3, so on, up to the last distinct data value in your population could be xk, the kth x value. And then as we already have seen throughout our understanding so far, then the right-hand side column here is to indicate different probabilities corresponding to when your random variable x equals x1, when your random variable x equals x2. So here's I'm filling it out. So probability when capital X equals x1, that's what we put in on the right-hand side column corresponding to that same entry. And here, probability when capital X equals x2, and that is the same corresponding entry when x being x2 right here, and so on and so on. So this is generally a probability distribution. And of course, provided that we add up all the probabilities here and already ensure that all these probability values add up to 1. And then at our last entry here, probability when x equals the kth x value is there. And so now, if we look back into our work previously, in just now happened, then the mean value seems like the new method we came up here is. Population mean is found by we look through our table here. We're looking at our probability distribution, and first value distinctively is being x1. I am going to multiply the value with the corresponding probability when your random variable equals x1 as a product. And I'm moving on to the next one, namely x2, and I need to multiply that value on the left-hand side with the probability value on the right-hand side equals x2. And I'm going to keep advancing. I'm going to keep adding until I reach to some of my ending one here, namely x kth, or the kth x value multiplied with the probability when x equals x of k right here. And so really I ran out of space here in my writing board, so I have to write it down here. But really, if you have more space in your own paper when you're taking notes right here, then it's really just one formula that keeps extending further out to the right-hand side. And then this work we're doing here will end at the kth value distinctively on our list right there. And so the mean value here, once we come up with the final value, we are going to use a symbol mu over here. So what happened here? X bar used to be used as mean, but now we switch from using X bar to this new symbol over here, because remember, what I stated earlier is what we're looking for here is the kind of mean value for a population. And so, and I will come back to explain the difference between X bar and mu over here. But for now, anytime we are calculating population mean, we must be using the mu symbol. So mu here is the population, or the symbol for population mean value. And there are tons of website resources showing you how to draw the mu symbol. This is just my style of writing it, but you can look it up on Google and it will show you how to write a mu symbol. But pronunciation, so this is say mu. So what exactly is a mu symbol? The mu symbol is simply a lowercase Greek letter m. So it stands for mean right there. So lowercase Greek letter m. But and we use that lowercase symbol, that lowercase Greek letter m right there. Now we call that mu right there, is to represent the way how we find population mean. So we made it to a new formula. So calculating the mean value, same fundamental, started out, added up all the values and divide by how many there are. But now, surprisingly, we derived a new formula. We recognized a new formula, and this new formula here, throughout our example, you're going to find out that it is particularly good in the case where instead of having the full complete list of data, you're only given as a probability distribution. And so this formula of how you can find the population mean is a good place for calculating the mean value when you are in a probability distribution like that. Okay, so after we learned a new method to find population mean value, now we are ready to make our way into discovering a new method to calculate population standard deviation. So population standard deviation. And so strictly speaking, anytime we're calculating standard deviation, we must have a mean value found previously. And so here to once again to recognize the new method to find population standard deviation, we're about to use that same data 1 again. So I'm going to apply the skill we're learning here on data 1 again. And we remind ourselves that right before this we were finding mean value, population mean, treating regarding data 1 as a population, and mean value of data 1 is 76.3. I mean, we actually found this calculated value of the mean value for data 1 is long ago, but here we're pretending now that data 1 is a population data. So I'm still going to rewrite that note here. Data 1 is being pretended as a population data, even though it's not that realistic here because data 1 is quite small. We have an n number being only 40, but we just simply need to learn how the concepts work and how the formula is being derived here. Okay, and so now our traditional formula for calculating standard deviation comes back here. Once we had the mean value, the way to calculate standard deviation, and remind yourself that standard deviation is defined, is to be understood as the average of all differences between values and the center and the mean value. And so now I'm going to look at 60, my first value, and I'm going to subtract the mean, 76.3. And in our work previously, we've learned that we're going to need to take the square of that, and then there are going to be 3 60s in our data, so consequently we're going to have 3 different squares like that. So 3. And then we are going to have the next distinct item here is going to be 64. So I'm going to subtract 64, subtract the mean, 76.3. I'm going to square that difference there. And there are 4 value in my list, and so I wrote this a little too narrow here, so I need to write it down further out. So 64 minus 76.3, and I'm going to square that difference there, and then there are 4 of my 64, so consequently it will bring me into 4 of those squares right there. And we add up all the squares, so we add all squares of the differences between value and mean. And then I'll keep doing this for a few more items. So the next one here is being 68. I'm going to subtract 76.3 the mean, and I'm going to square that. And then 68, I have 5 of those squares consequently being produced. And I'm going to keep adding that. And the way how we find standard deviation, we keep doing that until we hit a couple of all of our ending ones here. So 1 times of the 104 minus 76.3 square, and then the last one here is 1 time of that 124 minus 76.3 square. And we used to know that when it comes to finding standard deviation, we need to divide by 39. That was our rule that we've learned previously. I mean, prior to this point here, it was 39 simply due to the n number minus 1. That's the explanation for that. However, in this time, we actually are going to, so we're no longer going to divide by n minus 1. Now keep in mind, our goal here is to calculate standard deviation of a population data. So now the different work we do in here is we're actually going to divide by 40, so you're complete. So here we're talking about the n size, the n number being 40, But even if you have the actual data of the entire population, then we're still going to divide by all that, how big the data, how big your population data is. And so take that from me right here. When we're taking the population standard deviation, then the first thing we have to switch is we switch from n minus 1 in the denominator, we switch to the actual n number. And then after doing that, then the usual square root is going to kick back in. It's going to come back in, and we're going to take the square root of all that inside. And so, but of course, this is not our final formula. So don't take that as a final formula yet. Let me take a pause here and explain the reason why a little bit about why we actually now going to decide to divide by n instead of n minus 1. First thing, divided by 39 in our example here, or generally by divided by n minus 1, is not wrong. But now, as I already said, we are pretending that data 1 is a population data. Apparently speaking, the data size, or how big data 1 is, being 40 pieces of data, is quite unrealistic for being a real population data out there. Only 40 pieces of data is too small for being a real population data out there. And so when we're talking about if you actually know the real n count of a real population data, then we have to imagine that the n number right here is really a huge number. I couldn't even say up to the millions. Millions is probably not even as large as the real size of a population data. And so as we start having that imagination that when we really are working on a real population data where the population size is so big, the n number really is a huge number, then back to this sums of all the squares right here. If we were divided by n minus 1 or divided by n, it will make almost no difference. So these two, when we're talking about data being in the tens of millions, then the squares of difference, I repeat, that the squares of all these differences, the sums of all the squares of differences divided by either n minus 1 or divided by the actual n makes no difference. The difference there, realistically, the difference there is too small to the point that we can completely ignore it. However, choosing to divide that sum of squares of differences that we've seen, choosing that to be divided by this n, right, the actual n count of your population data, and pretended that you actually somehow have that actual n count of your population data, then choosing to divide that sum of squares of the differences by the n count is going to give us some advantage for the next step. So here simply just to produce, so doing this, divided the sum of squares of differences divided by n right here, doing this is going to give an advantage for the next step. And you will see that next step as I explained in my following part of the video. Alright, so after some explanation, I hope it was clear enough, and you can always clarify me by either comment on my video here or send me a message to ask me if you need some more clarification about my explanation of why we are actually switching over to dividing by n. But now, that advantage I said in the earlier in my explanation now is that right here inside of my square root, this fraction once again can be turned into, now I'm still going to retain the square root here, but let's go ahead and look inside the square root. It's a fraction, multiple terms in the numerator, and each term here is a square of difference, and we added up all those squares right there. But now I'm going to, similar to the work that we found mean earlier, I'm going to break it down into multiple terms. So here 3 times 60 minus 76.3 square over 40. That's how I produced my first term out of that huge fraction. Then I'm going to move on to my next term. It becomes 4 times 64 minus 76.3 square over 40. That's my next term. And I'm going to continue into my third term, being 5 times 68 minus 76.3 square and divided by 40. And so now you can see where I'm going from here. I can just keep producing other fractions, and each one of them is the multiple count, the frequency count, multiplied with the actual difference between value and mean, and then I keep repeating that until I hit to my last difference, the last squares of difference in my list. And so that's what the dot dots here represent. And so now one more step right here before I make my ultimate connection with the final formula. But so the square root still remains all the way. And so in my first fraction, I'm going to produce, I'm going to purposely rewrite my first fraction as 3 out of 40 multiplied with 60 minus 76.3. And as I'm writing this down, I need everybody or anybody who's viewing this video to start thinking about what's the connection between that 3 out of 40 with the probability distribution we're currently having on the computer screen here. And so now back to my current formula. The next term, the next fraction I have inside my square root in the previous steps here, I'm going to purposely rewrite it as 4 out of 40 multiplied with 64 minus 76.3. Square, and the same work is going to be continued for the other fractions. So here my third one is going to be written as 5 out of 40 times 68 minus 76.3 all square, and keep doing this, repeating this until I get to my last one inside the square root, being 1 out of 40 multiplied with 124 minus 76.3 square. And so now when we're at this step right here, I have to admit, if I spend all that time deriving with all the crazy math right here, you're gonna feel it's a waste of your time. So I'm gonna let any of you, the viewer of this video, to recognize this on your own. But it will take about a few more algebra steps, and that's what I'm writing the vertical red dots here is for. It's going to take a few more algebra steps. But remember, I'm not talking at all about pull out a calculator and get these squares being calculated. But I'm talking about doing an actual algebra work. It takes a few more algebra steps, but eventually, and we're still inside of that square root. In the next step, in the later steps, about 3 or 4 steps later, after about 3 or 4 algebra steps, your part inside that square root now is going to be like this. The first term is actually reduced. That's why I'm saying all you need is just to find out and recognize for yourself a few algebra steps right here. And I have done this for my formal statistic courses for about over 10 years here, and my students have always been successful finding on their own the algebra steps to recognize how I make the connection from here to this final formula right here. So any viewer out there who view this video, you're also welcome to find out what the algebra steps here that I'm kind of hiding here in my video. But the first term, after a few algebra steps, working with all these terms together, the first term surprisingly or shockingly reduced down to 3 out of 40. Okay, so that 3 out of 40 is still there. The probability, you can start thinking about this is nothing but just the probability of your value 60 on the probability distribution table. But now the squares here is actually reduced to a shockingly, that value 60, and we're completely skipping the subtraction. So 60 squared. Then I'm done with the first term. Then I'm going to move on to the next term here. The next term also reduces down to 4 out of 40 times, but instead of the difference here, it reduces down to 64 squared, just the value on the probability distribution being squared itself. Plus, and the next term here, what remains there is the probability 5 out of 40 multiplied with the difference, the square of the difference between value and the mean, now reduces down to only 68. So it looks like in any of the term currently we completely skip the subtraction. We skip the subtraction of the mean value, and we keep adding all of these pairwise products until the end of our list being, so our last term here reduces down to 1 out of 40 and multiply with, so that square there, instead of the square of a difference, now it's only the square of the individual value, 124 squared. But we're actually quite not done. And of course, we're still inside the square root, but allow me to extend a little further on the left here on my square root so that I have a purpose there. But after we're done adding up all of these products between square of the value and the probability correspondingly, square of the value and probability correspondingly, after we finish adding, we are still going to subtract the mean value, but only one time. We subtract the square of the mean value, so 76.3 square is being subtracted from that summation work. And this right here is our new formula for calculating the standard deviation, the population standard deviation. All right, so let me take a pause from that earlier work directly with data 1, but now let me look into a separate space right here. But what is the generality we have seen in that very last step that I did in my data 1 in the work of finding the population standard deviation? So it looks like, and if you're already forgot what happened at that earlier step, feel free to pull back on the video here. Feel free to scroll back and look back at that work. But it looks like the first term came out inside of that square root. The first term of the summation really was just the value x1 in the probability distribution being square. So the value x1 being square, and we multiply with the corresponding probability when x equals x1. And x here, I mean the capital X, the random variable. Then we advance over to the next entry, simply square the value x2 square. Square that value x2 and multiply that square of x2 with the probability value when x equals, when capital X equals x2. And we add these two, and we'll keep doing this. We'll continue doing this. For x3 square, multiply with probability when capital X equals x3. And we'll continue doing this. And like I said again, I inconveniently, my board space is short, so I can't write any further out to the right hand side, but think about when we're actually doing the work, we just continue further to the right hand side until we hit to the end of our list of our distribution, our probability distribution. So here it's xk, the kth value being square, multiplied with the probability when the random variable x equals xk. And once we are done adding up, we are going to subtract one time the square of the mean value. And after the subtraction, we are going to take an overall square root inside of that. And that is a new formula we recognize for calculating population standard deviation. And so in a cleaner space here, let me just simply rewrite that formula for the population standard deviation. But what's going on there, that generally from any probability distribution, all you need to do to calculate the population standard deviation is that we go x1 square multiply with probability when random variable capital X equals x1. And we move on, repeat x2 square times probability when capital X equals x2 plus, then we move on to the third distinctive data value x3, square the value, multiply with the probability correspondingly for x3. And then we keep doing that until we reach the last one in our data, being xk square multiplied with probability when random variable x equals xk. After we're done adding, then we are going to subtract 1 time the square of the mean value, and then we're going to take a final square root. And I purposely write down my formula this way so that you can see there's a certain order of operation, and the closer you stay with the order of operation, it's going to get us a successful answer. And so now this new formula is the formula to calculate population standard deviation. And so population standard deviation use a symbol sigma to indicate a population standard deviation. So anytime we are calculating population standard deviation, let's use a sigma for population standard deviation. So we used to use lowercase s, but lowercase s is not the right symbol now for population standard deviation. So anytime we're calculating population standard deviation, make sure you use this symbol over here. It's called sigma. And sigma is a Greek lowercase letter s. So it's still s, but it's not the English version. So English version we saved that for the smaller kind of data, the kind of data where we know the n count. And here, when we're calculating population standard deviation, then we're going to use the sigma symbol. And so consequently, this formula right here we are just derived right here is a formula that calculating our sigma value. All right, and so back to this work, we were almost done with calculating the population standard deviation of data 1 right here, pretending that data 1 was a population data. Then the calculation came out after this calculation here is being a 12.34 here. And so as I said in my generality earlier, that this value here we regard as a population standard deviation. So symbolically it equals sigma. That's our sigma value, population standard deviation. Now, if any of you viewer out there who have also seen my other video on calculating standard deviation of data 1 by regarding data 1 as a small with considering using n number being 39, I mean the n number being 40 but n minus 1 in a formula, then that standard deviation pretending data, I mean that standard deviation when our data was small, having a known count, it's a 12.5 5 here. So the answer has been a little difference between these, and of course that makes sense because we calculated this S right here almost the same in the formula, but remember these 40 right here because we divide by the n number, but before, back then, we were calculating based on n minus 1, which was only 39 in the denominator. Now that we work with the population data, where our data is now represented as a random variable with a probability distribution, where it's listing out x1, x2, x3, and so on and so on. All these values are the distinctive value, the distinct value, the unique value of the random variable x, and the right hand side column represents all the associated probability when the random variable equals to that distinct value on the left hand side. So p in parentheses x equals x1 is the probability when random variable x, capital X, equals x2 in particular. Probability when random variable equals x3, and etc. and etc. So once again, our population data is being represented by a random variable and having a probability distribution like this table is indicating, and provided that we already verify that the probability distribution here is a valid probability distribution. And so mean value can be found by x1, the value on the left hand side column, multiplied with the probability correspondingly on the right hand side column. Now with that product, we're going to add to the product of x2, multiply with the probability on the right hand side. Plus the next product, x3 times the probability where random variable x equals x3, and we keep adding all of these pairwise products from the beginning to the end. So let's say your data here has k, some k distinct values, then this is, or technically the last one, then we're going to add all these pairwise products until we reach the very end of our list here. So xk, or the k value, the ending value in our list, multiply with the probability where random variable x equals x k. That is how we find a mean value. And so mean value has, and the kind of mean value here, understand that the mean value here is designed, this formula, this new formula is designed to handle the situation where we don't have the actual list of the data. We don't know the n count of the data. We only know the probability. It's this random variable only gives us a probability distribution. We only know the probability distribution, but we don't know the n count. So this formula for calculating mean is intended to calculating the population mean. So we refer to this mean value here as it's a population mean value. And so we use the symbol mu. And so here in this formula, mu equals that calculation. And in many textbooks, as well as on many websites, this same formula, calculating the population mean value, is written in a different form using a summation notation. So that same formula is now written as x of I multiplied with probability where x equals x of I. So each of these pairwise products and all of those pairwise products are being summed up from the beginning index 1 to the last index k right here. And so this summation formula gives the exact same answer of the population mean. So I am not particularly requiring anyone to follow which formula. It's all exactly one same thing to do one same work. So for viewers and my students of my class right here, you guys can use whichever formula that you are more comfortable with, because getting the truthful understanding is what's more important. And furthermore, once again, with our population data being represented by a random variable x, capital X, and this table like this is a probability distribution of your random variable, and now pretending that we already found a mean. So we got a found population mean, or known population mean. Then what is our standard deviation? Or now precisely speaking, we refer to this as population standard deviation. And the formula we are using here, the formula we discovered here, is that it's going to be x1 square multiplied with the probability when variable x equals x1 plus x2 square times probability when random variable equals x2, and etc. and etc. We keep adding all the pairwise products between square of the value on the left hand side multiplied with the corresponding probability to the right hand side, and then we keep adding to the and pair to the left, to the very last pair here. So x of k, xk, or the kth x value square multiply with the probability where random variable x equals xk. But now, once we finished adding, then we are going to subtract the square of the mean of the population mean. And notice we only need to subtract once. And after the subtraction, after subtracting square of the mean value of the population mean value, then we take a final square root. So that complete formula right here is the way we find our population standard deviation. In population standard deviation, we use a symbol sigma. And sigma, once again, is the Greek lowercase letter s right here. It's Greek lowercase letter s. And so here in our formula, for this population standard deviation formula, sigma equals that formula. And again, the same formula here, but in many textbooks and on many websites, in this same formula is written in a summation notation. So here we're looking at summing up all of the square on the value individually with the corresponding probability when random variable equals to that indexed I value, but we need to sum all of those pairwise products from the beginning 1 to the kth index right here, and after the summation we are going to subtract mean square, the population mean square, and we put that work in a, or that calculation in a square root. So that is a different form, this different way of writing this population mean formula, but they are truly one. And so like I said again, whoever viewing this video, if you are more comfortable with using the summation notations, feel free to use it. If you are more familiar with this, or more comfortable with using this formula here, it's a little longer, I admit, but it does have an advantage of it. It shows clearly what to do with each of these pairwise products right here, and it's more step by step, but they should all ending up with the same exact result, the same exact answer. Alright, and so we are now ready for our third example. And once again, I'm still using that exact same data, letting capital X being the random variable representing the age of a student at HD College. So once again, the intention here is that X represent a population data. And so this table right here is the given, so think about some super powerful computer at that HD College already provided us the probability distribution. So probability distribution is now a more convenient way of viewing large data, very large data, instead of seeing the entire list. So once again, let me clarify a different understanding that I've had people questioning me. So now if I'm talking about there's a computer that's able to store data this large, and why not giving us the complete list? But think about if that really happened, where the computer does give you a large list like that, and how many people would like to see that list? And so when data become once again that big, where we ignore the n count, it really means it's too big, even though there is a list available. We just simply we should be better off by reading a probability distribution like this, so that we have a more general idea of the data, rather than just looking through the entire list one by one and count and knowing how many 17s, how many 19s, and so on and so on. And that's the whole point of using, again, that's the whole point of using random variable, and it's a very convenient way of representing the population data. But so now, into this example, then first question I'm going to bring up, question A. Let's find the mean value of the random variable X. And so as soon as I finish writing down the question right here, have that clear understanding that the intention for this problem, finding mean value of X, is to find the population mean. That mean we're looking for here is intended to be the population mean. Simply because the data here we already ignore, and we never ask for what that n count is. So if you are going with this route right here, and I have seen people doing that in my classes, and I've seen people doing that commonly out there as a mistake right here, but 17 plus 19 plus 21 plus 23, and hey, there are 4 values being listed. Yes, this is a list, but it's not the list as a list of the data. It's just the list of all the distinct value, but then correspondingly it came with these came with the probability associated. So if we are only dividing by 4 here and claiming that this is our mean value, we're way off the hook right here. So this is the incorrect way of doing that. The correct way now is to produce, and even though I introduced the summation formula earlier, but I still prefer to use the written out formula right here in this work, so that more people are able to follow the steps right there. So to find the population mean, once again, we look at our first data here, that distinctive data value for the random variable x being 17, but now we are going to multiply with probability correspondingly being 0.2, and so we're done with the first pair. The next pair, now we're gonna need to add to that first pair with the next pair being 19 as the value, multiply with probability 0.25. And the third pair here of value, we're looking at 21 as being the distinct value and probability being 0.45. And the last pair, and we're done. 23 on the left hand side is the value distinctively, and the right hand side is that probability correspondingly being 0.1. And so now just simply give a calculation here. So calculation shows mean age on this HD college right here, at that HD college is 19.9 years old right here. And now what we found here is once again the population mean value. The population mean, because we calculated the mean value out of the entire population data, not only a small set of data. Now, before I'm moving on to the next question in the same example here, I need to make another note. So, in a different video a little while ago, then I posted an instruction of how to use the stats button with a TI 83 or 84 calculator. Now, I have to really clarify in case anybody is falling into that mistake right there. But calculating population mean from a given probability distribution like this, there are no technology that can help you with that. So this route using the stats button on the TI 83 or 84 calculator will not work on this. The reason is simple. The stats button in your TI 83 and 84 calculator can only find for you the mean value once you already have the complete list of data and given to the calculator. But here what we have is only we don't have the complete list. What we have is the probability distribution. So we did not, in other words, again, I have to remind everybody that this table is not writing out how many 17s there were in the data, how many 19 there were in the data. This data did not tell you that. It only tells you that 17 in the data is happening at probability 0.2. 19 as a value happens in this data X right here at probability 0.25. And so, as a matter of fact, not too many technologies out there outside of the TI 83, 84. There are not too many technologies can handle the calculating probability on a probability distribution like this. So make sure you know how to use the formula. And normally, when it comes down to a probability distribution, then usually our work for finding mean value is quite short, and we already skipped. We save ourselves from too many operations, so we only have simply just adding and multiplying, no more division. So it shouldn't take too long. And so only use your calculator to help you calculate, but it won't have any direct function or feature to handle this population calculation. All right, and so now we are ready for part B of this same example. Example 3, now we're looking at part B. So we would like to find the standard deviation. This data X right here. So this is one gigantic data, which is simply represented by a random variable X. But so this standard deviation here, once again, I need to remind that it's intended to be, our intention here is to look for the population standard deviation. And And so symbolically, it's that sigma symbol that we're looking for. Okay, and so as far as the work, once again, and I have to warn any all viewers ahead of time, but once again, we won't have any fast technological tools to help us with this, because what we have here is not a complete list of data. We only have here a probability distribution of the data. So we must use the formula. So 17 square times the probability 0.2. That's the first step. And then we're going to add the next one here is a pairwise product of 19 square times 0.25. The next one, 21 square times 0.45. The last one in our sum is 23 square times 0.1. But now, and you can see that I'm writing down here in particularly a certain order so that it keeps your work safe. So after we finish adding all the pairwise products, then we're going to subtract. And keep in mind, we already found the mean value from part A, and so mean value was 19.9. So now we're going to subtract the square of 19.9. And then after subtraction, we are going to take an overall square root. And that is how we're calculating our population standard deviation. So sigma equals with that square root quantity. And so now I'm ready for the final answer. Calculation comes out to be 1.84. And that is how we're calculating our population standard deviation. And at this point, after studying carefully all about the population data, then we're going to start asking ourselves, so what about those data with the n count? So let's say think of your data 1, it has an n count being 40. Think of some other data set that has an n count. But so now a rule of thumb is when your data has a known n count, because when it's a population and the n count is too big, that we have to ignore it. So when we're working with any problem that having an n count, then usually it's a small n count or some value that we can count through. And so if those data are being have an n count over here, then we regard to those as sample data. So data having an n count is now regarded as sample data versus population data. So we just now learned population data as we have to ignore. We must ignore n. But so now, if we're looking back at any data we have been working prior to this point right here, then those data are regarded as sample data, where they have known n count. And so for now, we're just beginning working with population data and making that clear differentiation between sample data and population data. One major difference is that sample data has a known n count. And the reason for this, because sample is usually, and that's the whole point, we can never pick a sample that being as large as the entire population. Usually much smaller than a population. And that's why when it's much smaller and later on when we formally learn about picking up sample data and picking or learning about doing sampling of the data right here, then we're going to learn the reason why sample has to be much smaller than the population data. But so for now, since our journey just about begin distinguishing between population data and sample data, and all we have to keep in mind is population data is the kind of data being so big that we ignore the N count, and in the sample data, then it's something that we actually collect, and so and it's a lot of time much smaller than a population data, and so in that way it's a good place to have a known N count like that. After making a clear explanation the difference between population data and sample data, so we can categorize our understanding into a table like this. So of course numerical data we're working with, but so now it's being split into two different settings. So our data could be either a sample data or being a population data. So data can be a sample data, something small with the N count. So what we know is being a sample, just like what we've learned moments ago. That sample being a sample data, we have a known N count. And for population data, we have to ignore. We haven't ignored N. It's there, it's out there, but it's so big that we have to ignore it. So as far as the size of the data, we have a known N count for sample data. We have an ignore N count. We have an ignore population size, because it's impossible to get that. And then in either settings, either you are working with a sample data or you're working on a population data, we can always find a mean value. So mean value in a sample data is regarded as a sample mean. So sample mean here, beginning of the quarter. So now if you're looking back, then so all that time throughout the beginning of the quarter until now, we have been using this symbol for X bar. My intention is to start out teaching stats, always approach things as a sample data, so that everybody has a nice clear understanding. And then now once everybody has a clear understanding, and then it's time to move on to the population data. But so, like I said again, sample data or mean data, we can always find a mean value. So mean value from a sample, or now regard namely as a sample mean, we use the X bar, the lowercase x with a bar. That's the sample mean symbol formally for sample mean. And so we just now learned throughout this lecture that population mean, see, it's a population data, no matter how big, but we can find a mean value. So mean value of a population data regarded as a population mean, we use symbolically a mu symbol right here. And same way, once we found a mean being the center of the data, either in a sample or in a population, mean always for being the center of the data. And so once we pass center of the data, then standard deviation need to be calculated, average spreading of how data values being spread away from the center. And so now if your data is being a sample data, then we can find the standard deviation of a sample data. We namely refer to that as sample standard deviation. Symbol we use for that, that's the symbol we've been using throughout the quarter until now, lowercase letter s. But now when your standard deviation become a population standard deviation, or in other words, if you're calculating standard deviation of a population data, make sure you are indicating with the symbol sigma right here. And notice these two are actually, they're all having different formulas to calculate. Mean value will always turns out similar, no matter if you have small data or big data, but the mean value will turn out the same. But standard deviation, you've seen in the work that they turn out differently. So there's sample standard deviation and population standard deviation.